Welcome to Pomodoro Joe for Sunday, June 11th, 2023. Today we're doing LeetCode problem 1146, snapshot array. This is a medium problem. Implement a snapshot array that supports the following interface. Snapshot array takes a length that's an integer, initializes the array-like data structure with a given length. Initially, each element equals 0. Void set index value sets the element at the given index to be equal to val. Int snap takes a snapshot of the array and returns the snap ID, the total number of times we call snap minus 1. All right? And finally, get takes an index and the snap ID, returns the value at the given index at the time we took the snapshot with the given snap ID. All right, and that is it. Then we have some constraints. Okay, this one seems pretty straightforward, so we will put 25 minutes on the Pomodoro timer and get started. So my initial thought here is we'll keep track of our current set of data, which will just be our array. Every time we take a snapshot, we can add that to an array of snapshots. Then anytime we ask for those snapshots back in the get, we just can look up that entire array in our array of snapshots. It takes a lot of memory, but I don't think there's a ton of data we're storing here, so it should be okay. Well, let's find out. So we start with our storage. I'm just going to call it data. And for this, we will make it an array of zeros times our length. Let's see, we'll also need to keep track of our snapshots. So I'll have snapshots. And that will just be an empty array to start with. And we need to keep track of our snap ID. So let's keep track of that. And that'll be 0 to start with. Okay, so I think that's all the data we need. Then when we do a set, we'll set our current data. So self.data at this index. And we'll set it equal to the value. I think that's all we need here. That's pretty straightforward. All right, then when we take a snapshot, we will add our entire data array to our snapshot array. Let's see, we just need to append. This will be our self.data. And then we'll increment our snap ID. And then looks like we have to return snap ID minus 1 here. So we'll do that. All right, and now in our get, we just have to look up our snapshot in our snapshots array. So let's do that. So we look up the snapshot first, so that'll be the snap ID. And then we look up the value, which will just be the index. All right, and I think that is it. We have some storage. We'll keep track of our current data. Then we'll keep track of all our snapshots and our current snapshot ID. Anytime we update the data, we just update the data. Whenever we take a snapshot, we just add the snapshot to our snapshots array, increment our snap ID, and then return that snap ID minus 1. Finally, in the get, we just look up that snap ID in our snapshots and return the value at the index. Let's see if this works. Oh, and we get the wrong answer. Oh, So this is the trickiness with Python and reference values. So what's happening here is whenever we put this data into our snapshots array, this data is the same array every single time, and that's shared across every snapshot. That's going to be a problem. That means if you change this data, you're actually going back and changing all of your snapshots. So what I really need to do here is data.copy. All right. Yeah, that's the trickiness with Python, or one of the trickinesses with Python. Okay, that seems to work. Let's see if we can pass all the tests. Oh, memory limit exceeded. Whoa. So we will use this test case. And yes, I can see we've exceeded memory. Okay. So let's take a look at our snapshot array here. So our snapshot array is not super efficient. We're storing a bunch of zeros. And for all these zeros, every time we take a snapshot, we're storing them again and again. So we are storing entire snapshots, which is not efficient. We're also storing these default values, which is not efficient because we know what the default value is, so we don't need to store it. So there's a bunch of things we're doing here that are not very efficient. Let's see if we can eliminate some of these inefficiencies. So instead of storing this data as an array, let's store a dictionary that represents the current state of our data, or maybe the current delta of our data. That way we know everything is 0 unless we have some value in our dictionary that tells us otherwise. Now the dictionary, the key will be the index, so this index, and the value will be the value. So that'll be our data here. So that'll eliminate all of these zeros. That's a little bit helpful. So we take our data, we store it in a dictionary. So then here, we don't need to change anything. Our data at the index will just be our value. That's great. So this is just storing the deltas now. Now let's see, when we take this snapshot, we could actually keep this, but then we don't necessarily have a value at an index. So this is a little bit trickier because now that we don't fill this with zeros for all of our initial indices, we might have some get that's trying to get a value that we've never set. So we'll have to return 0 if we don't have that value. So we'll have to do something like if snap ID is in our snapshots, well, let's see, our snap ID will be there, but that's if index is in snap ID. Otherwise we return 0. Okay, so now we have some data. We'll be keeping track of our changes. Every time we make a change, we'll just set it in our data. Then we'll make a copy of our data here. Take the snapshot. So this might be a little bit more efficient. Let's see if this works. I'm not convinced this is going to work. Okay, so that works. Let's see if we can pass all the tests with this. So we're eliminating all of the default values. That should save us a bunch of space. But we still have a memory limit exceeded. We're doing better than last time. We're beating 72 out of 74. So let's see, grab that test case. All right, so we still need to eliminate some of the inefficiencies in our snapshot array. All right, so we're still storing full snapshots for every single snapshot we take. We don't necessarily need to store the full snapshot. We could just store the delta of the snapshots. That way, down here, it makes this a little bit more complicated because we'll have to find, I guess, the previous snapshot if we don't have a delta for the snapshot they're asking for. Let's see. So let's put some notes here. So key is equal to index, and val is equal to the value at that index. So the snapshots. So currently, we're just keeping track of full snapshots here. Instead of keeping track of full snapshots, we can keep track of the delta of the previous. Isn't that what we're doing? So yes, now instead of keeping full snapshots, we'll just keep track of the delta between snapshots, which means that this is going to be a little bit more complicated. So let's see, the index here will equal the index, but the value, that's going to be equal to, let's see, we'll have to keep an array of all of our snapshots. So array of snapshots, of snapshot deltas. Well, let's see. This will be a snap ID and the value at that snapshot. Okay, so here's what we're doing. Our data, we'll just keep track of the current set of data. So the delta between the last snapshot and the current snapshot. So this is just going to keep updating, which means that we will actually have to reset this data to an empty dictionary every time we take a snapshot. So this is just keeping track of the deltas. Then in our snapshots array, each value in the snapshots array will be an array of all the snapshots that we've taken, but only with the deltas. So essentially, every time we have an entry in this array, it will have the snap ID and the value at that snap ID. And we only keep track of the times that it changes. which means that if we're looking for a snap ID that happens between changes, then we'll have to do some type of search inside of the snapshots array for the proper snap ID. And so now our snapshots array, this will contain basically one array for every entry in our length here. So we'll basically have an empty array for blank in range length. Okay, so again, this index will be the index of the value that we're looking for, and the value there will be an array of all the snapshots in which some change occurred. All right, so we've got that. We still have a snap ID, that doesn't change, this snap doesn't change, but now here we don't just append a copy of our data anymore. We'll have to go through for every change that occurred, so for every index in our self.data. So these are all the indices of values that changed. So these keys represent the index of a changed value. Then our snapshot at that index will be updated. So snapshots for this index, we will append, but we don't append our dictionary now. We'll append a tuple. This will be the self.snapID and the value for our data at this index. So that's self.data at this index. So that's our snap ID and our value. And then we do need to update our snap ID at the end and clear our data, and we return our snap ID. All right, so this is starting to shape up a little bit. We'll update our snapshots, again, storing a new snapshot for every changed value. Then down here, we can't do this anymore, unfortunately. This gets a little bit more complicated. So now we have to find our snapshots. Let's see, we'll start with our result as 0 because we do have our default value here. Now our snapshots for this index, that will be self.snapshots at this index. And now for every element in this array, we need to check for essentially a snapshot or the previous snapshot. Okay. So we're just going to go through every single snap in our snapshots, looking for the one that's less than our current snap that we're looking for. All right, I'll explain this one a little bit better here. So we're going through all the snapshots for this index. We're looking at every snapshot and that value. If this snapshot is less than the snapshot that we're looking for, then it's potentially the one that we're looking for, and we'll just set the value. If this snapshot is greater than the snap ID we're looking for, I guess if it's less than or equal to, there we go. If it's greater than the snap that we're looking for, we can actually break out. So we can actually do this if we want. And at the end, we'll just return that result. All right, let's see if this works. Let's see. I missed the in. There we go. Try that. Okay, that seems to work. Let's see if we can pass all the tests. And we pass. We don't do great though. So we pass, we only beat 8.4% for runtime and 78% for memory. That's pretty good with memory. All right, I am down to 3 minutes, but I'll show you a quick thing that we can do here. So right now we're doing a linear search through all our snapshots. Now we know that these snapshots will be in ascending order. So the earliest snapshots at the beginning, the later snapshots are at the end. We don't have to do a linear search here. We could do a binary search. Now I could show you how to do binary search really quick using some built-in tools that Python gives you. Now other languages don't necessarily have these tools. You can do your own binary search with a low and high and search for the mid, but we can use Python's built-in tools to help us out here. So we have our snapshot. I'm going to use bisect. I'll call it snap. We can do bisect, and what bisect will do is actually do our binary search for us. So bisect.bisect, and I'm going to do a bisect right. So I'm looking for the insertion point of this snap ID somewhere in our snapshots. So call snapshots. And let's see, I will have to pass in our snap ID here. So this is looking for the insertion point of the snap ID in our snapshots. Now our snapshots is a list that has tuples, so we have to actually specify which key we're trying to insert the snap ID into. So our key here will be lambda x, and that is going to be x at 0 because that's where we're storing our snap IDs. And because we're doing a bisect right, we have to set our result equal to our snapshots at this snap -1, but that's only if it's greater than 0. Oh, and we're out of time. I'm just going to keep going here. So if the snap is greater than 0, else our result is going to be equal to 0. Okay, let's see if this works. So this is a binary search on our search space. This should be a little bit faster. All right, this should be snapshots at index 1. All right, let's see if this beats our previous solution. And we do significantly better with this search. So our previous solution, we used a linear search going through all of our snapshots. In our second solution, we used a binary search using Python's bisect method to do a binary search. So previous solution, 8.4%. Bisect solution, 89% for runtime and 80% for memory. This is so much better. All right, check out bisect. It's a simple way to do a binary search. It's much easier than implementing your own. So yeah, definitely check it out. All right, I am totally over time, so I hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.